My name is Jeffrey Frankel, and in this series of YouTube videos I will show you techniques and tips to reduce the time it takes to deal with questions in paper 1 of the IB chemistry exam at both standard level and higher level. In which species does sulfur have an oxidation number of 0? All elements in their elemental state have an oxidation number of 0, so you're simply looking for sulfur, and there you go, S8. And it doesn't matter whether it's S as a single atom or S8 as a molecule containing 8 atoms, or it's oxygen with 2 atoms, or it's neon with 1 atom in its molecule, or it's something like carbon in the form of diamond with tens of thousands, or I don't know, maybe hundreds of thousands of atoms in the molecule. If it's an element in its elemental state, the oxidation number is 0. This is another one of these problems where you should take advantage of it because it is so easy. Just remember that an element in its elemental state has an oxidation number of 0, and that's all you're looking for. And take advantage of these simple problems so that the time saved can be used more profitably for the more complicated problems later on in paper 1. In this case, we're simply looking for the correct valence of manganese. Now we know that oxygen has a valence of 2. There are actually 2 different ways of looking at this. Oxygen has a valence of 2, therefore if there are 2 of them in this substance, then the manganese must have a valence of 4. And when you write them as names, as systematic names, you use the Roman numerals 4. So that is clearly the answer. Just let me show the link with the previous problem. If you put MnO2, if you look at it, the Mn, let's have a look at the oxidation number of Mn. Mn plus 2 times minus 2, and minus 2 is the oxidation number of oxygen. So there's 2 atoms, there's 2 of them, and that will equal 0 because the total species has 0 charge, so that equals 0. So therefore Mn would have a valence of plus 4. Mn has an oxidation state of plus 4, which is the same as a valence state of 4 in this way of writing it. So we say oxidation state plus 4, valence state 4. Therefore this is the answer. When I look at this one, I know immediately that oxygen has an oxidation number of minus 2. So I can forget C and D. And then when I look at this one, I know that chlorine only has an oxidation number of minus 1 in Cl minus. Therefore, this must have an oxidation number of plus 3. So there it is. There is the answer within 10 seconds. Now let me prove to you that this does have an oxidation number of plus 3. We've got Cl2O3. There's 2 oxidation numbers of chlorine plus 3 times minus 2 equals 0. And therefore 2Cl equals 6. Cl equals plus 3. Therefore confirming that. Okay, we've now done oxygen. So we know oxygen in most cases has an oxidation number of minus 2, so it's one of those 2. We also know that hydrogen does have an oxidation number of plus 1. That is also always true, so it's one of these 2. You can think it's unlikely that phosphorus has an oxidation number of 1, so it's probably this, but let's prove it. So we've got H3PO4, so there's 3 times plus 1 plus P plus 4 times minus 2 equals 0, because there is no charge on this species, therefore it equals 0. So it's 3 plus P minus 8 equals 0. P equals minus 5, that's plus 5. P equals plus 5. There we go. So that proves that. But as I said, the only way P could be plus 1 would be if it was the species P plus. That would be the only way, but it isn't the species P plus. That doesn't kind of exist. This is very similar to the previous one. Oxygen minus 2, that's fine. Hydrogen plus 1 and plus 1, that's fine. So it's a matter of deciding is it sulfur plus 6 or plus 4. I think you do have to do the calculation here. So it's H2SO4, and it's very quick. That's 2 times plus 1 plus S plus 4 times minus 2 equals 0. It's 0 because there's no charge on that species. It's a neutral species. So it's 2 plus S minus 8 equals 0. S equals plus 6. So that's that. Again, it's another one which, if you practice these, you will find they are easy to do. Simply remember that oxygen always has an oxidation number of minus 2. Hydrogen always has an oxidation number of plus 1. And elements in their elemental state have an oxidation number of 0. And as I mentioned before, I minus, the chloride ion, as I mentioned before, the chloride ion, the bromide ion, and the iron. Oxygen always has an oxidation number of minus 2. Hydrogen always has an oxidation number of plus 1. And elements in their elemental state have an oxidation number of 0. As I mentioned before, the chloride ion, the bromide ion, and the iodide ion have an oxidation number of minus 1. Just remember those. This problem is a little bit more complicated than previous ones, but essentially they're simply asking for the oxidation number of iodine in the iodide ion and iodine in the iodate ion. And I've said before about the chloride ion, Cl minus, that has an oxidation number of minus 1, and iodide ion will have the same. The iodine within the iodide ion has an oxidation number of minus 1, and the bromine in the bromide ion has an oxidation number of minus 1. So we know, therefore, the answer is going to be either A or C. And we have to decide whether the iodine in the iodate ion has an oxidation number of either plus 7 or plus 5. And we have to do a quick calculation for that. So the way I do it is iO3 minus, and I break it up into those 3 parts, and that therefore equals minus 1. Because of the negative charge, it equals minus 1. And then the iodine is the unknown, plus, and there's the oxygen. 3 times minus 2 equals that. So I equals plus 5. Therefore, the answer is C. Something that you'll come across in other problems is the iodate ion. And you must simply remember that the iodate ion does have an oxidation number greater than minus 1. The only ions with iodine or chlorine or bromine in them that have an oxidation number of minus 1 is the chloride ion, the iodide ion, and the bromide ion. As soon as you see anything else, like iodate, or you see Cl2O3, or you see ClO3 minus, or you see BrO3 minus, know that these will have positive oxidation numbers for the chlorine, the bromine, and of course for the iodine as well. Now we have a salt, the sodium vanadate, and the oxidation number is determined in the same way as previously. It's a neutral species, Therefore, the total is going to be 0. Sodium will have a oxidation number of +1. Vanadium, that's what we're trying to find out, +3 times -2 for oxygen. Just let me say why the sodium has an oxidation state of +1. It's simply because we're talking about the sodium ion, Na+. So therefore, if there is a positive charge, the oxidation number is +1. If there were 2 positive charges, like Mg2+, the oxidation number is +2. If there's 3 positive charges, like Fe3+, then the oxidation number is +3. So there's a consistency in these numbering systems. I mentioned before, Cl-, the oxidation number is -1, and oxygen has 2 minuses, so the oxidation number is -2. Let's go back to this calculation, and we have V equals 5 +5. So we come to here. And if these numbers are in your mind when you're doing this, and these concepts are in your mind, then you can actually do this calculation in your head. You don't need to write anything down. And again, it can be done quickly. This one is a lot easier than it looks. In order to answer it, all you need to know is what happens to iodate ions when they're converted to iodine molecules. Are they oxidized or are they reduced? Because if you look at the oxidation numbers they offer you, they say they go from either -1 to 0. Now we know 0 is correct because iodine molecules have an oxidation number of 0, or it goes from +5 to 0. So we simply have to decide whether the iodate ions have an oxidation number of -1 or +5. Now we know they cannot have an oxidation number of -1 because iodide ion has an oxidation number of -1. If the iodide ion has an oxidation of -1, then the iodate ion does not have an oxidation number of -1. We know from previous problems with iodine in substances containing oxygen or chlorine in substances containing oxygen that the iodine will have a positive oxidation number. And so we can immediately say, okay, it's either C or D, because iodine in iodate must have a positive oxidation number, and it must be +5. So we look at that. We know the oxidation number is going from +5 to 0. In other words, the iodate ion is being reduced. So we go from here, see what happens to the iodine in iodate ion. It undergoes a reduction, and its oxidation number changes from +5 to 0. That is the only possibility. What I'm telling you with this one is that they give you a choice of oxidation number of the iodine in the iodate ion, and you simply don't have to do the calculation. You simply choose the most obvious one. You choose the +5 rather than -1. And then you realize that if iodine in the iodate ion is +5, then when it's converted to iodine molecule, it's going to be reduced. And immediately go to C. This is another one that if you practice with these kind of problems, you can see them very quickly. And in many cases, you can deal with them in less than 20 seconds or so. Okay, we're asked to see in which equation does hydrogen peroxide act as an oxidizing agent. And when I look through these, I see this one. Fe2+ goes to Fe3+. Fe2+ is therefore being oxidized to Fe3+. Therefore, the H2O2 is acting as an oxidizing agent without even bothering with the others. You can look through the others and decide that there is no oxidation taking place there, there is no oxidation taking place there, and there is no oxidation taking place there. In fact, that's a reduction. So this one is the only one, just because I saw that the Fe2 plus is being oxidized to Fe3 plus. Therefore, hydrogen peroxide is acting as an oxidizing agent. This is one of these where I know when I see Fe2 plus goes to Fe3 plus, Fe2 plus is being oxidized to Fe3 plus. And when I see SN4 plus going to SN3 plus, I know SN4 plus is being reduced. So let's look at the SN4 plus. We want to see it being reduced. So clearly it's not A. Here it is, C. SN4 plus undergoes reduction. Yes, that's true. And in the process, it's acting as an oxidizing agent of Fe2 plus. And let's mark that. Now, if you had looked at it from the other point of view, you looked at it from the Fe2 plus, first of all, we know Fe2 plus undergoes oxidation. So we go here, Fe2 plus does not undergo reduction. Fe2 plus does not undergo reduction. So there, the Fe2 plus, so B and D you could eliminate immediately, and you can eliminate A simply because it does not undergo oxidation. This is the kind of equation that can make your head swim. You've probably never seen it before. You probably have difficulty understanding what it's about. But the reality is that there are a few things you could look at when they're talking about SN2 plus. They're talking about whether SN2 plus is oxidized or it's reduced or it is the reducing agent, and they're looking at Cr2O7. Let's look at SN2 plus. That has an oxidation agent of +2 because it is SN2 plus, and this, just like earlier with the manganese dioxide, there the tin has an oxidizing agent of +4 because of the two oxygens. So SN2 plus is being oxidized. So SN2 plus is being oxidized, and therefore SN2 plus is the reducing agent. So it's not the oxidizing agent, it is the reducing agent. So that's possible. And SN2 plus is the reducing agent because it undergoes oxidation. Well, that's true. That is definitely true. Let's look at the Cr2O7 2-. These oxidation numbers are a bit more complicated to work out for the Cr within this substance. However, you could guess from the past that Cr2O7 2- acts as an oxidizing agent, and it's orange for those, and it is converted to Cr2 plus, which is green, and therefore the Cr2O7 2- is reduced to that without even calculating the oxidation agent. You just have to know that that is reduced to that. So Cr2O7 2- is an oxidizing agent, but it doesn't undergo oxidation. And Cr2O7 2- is a reducing agent. No, definitely not. So B, we come back to B is the only correct one. And fortunately you could see it by just noticing that SN2 plus is oxidized to SN4 there. And when you just find that statement, so the SN2 plus undergoes oxidation and is the reducing agent. Okay, so we're looking at the species on the left, and is it acting as an oxidizing agent? And the answer is, here, Mg is going to Mg2 plus. That is being oxidized. Therefore, the species on the left is acting as an oxidizing agent. There it is. Very quickly. You could look at some of the others, and you could see that the silver, the oxidation number of silver in this species, silver nitrate, is 1, and it remains 1 in that one. The oxidation number there is +1, and it goes to 0 there. So in fact, the silver is being reduced. In here, we know that chlorine as the element has an oxidation number of 0, and it actually goes here to -1, so the chlorine is being reduced. Magnesium, clearly, is the only one that is being oxidized. And it's one of those things you can see it immediately. Mg goes to Mg2+, it's being oxidized. Fe goes to Fe2+, it's being oxidized. Fe2+ going to Fe3+, it's being oxidized. Sodium going to Na+, it's being oxidized. Just let me do the other side. Chlorine going to Cl-, it's being reduced. Bromine going to Br-, it's being reduced. A redox reaction is where oxidation and reduction takes place at the same time. Now we can see that in this case, Fe goes from Fe2+ to Fe3+. So that, yes, is a redox reaction. Mg goes from Mg0 to Mg2+. That is a redox reaction. In this case, no oxidation or reduction takes place. Hydrogen and oxygen remain the same state in this. Oxygen remains the same state in that. So probably without even doing any calculation, the sulfur also would remain the same state in that as it is in that. So 1 and 2 are the only ones. Just as an additional thing to add to this one, if you'd seen immediately that that one is not a redox reaction, because the hydrogen remains unchanged, the oxygen remains unchanged, and therefore probably the sulfur would have to remain unchanged. Then you would know immediately 3 is not a redox reaction, and therefore it would not be B, C, or D, but it's only A. So there are two different ways of looking at this particular problem, but each way of looking at it can be done fairly quickly, 10, 15, 20 seconds at the most. Again, we look at this and we see immediately Sn with an oxidation number of 0 goes to Sn with an oxidation number of 4+. So 0 there, or oxidation number +4. So we know that Sn is being oxidized, and therefore we know nitric acid is doing the oxidation. So what are we looking at? HNO3 is the oxidizing agent because it undergoes oxidation. No, that doesn't make sense. HNO3 is not the reducing agent. No, so that's wrong. Sn is the oxidizing agent because it undergoes reduction. No, we know that's wrong. Sn is the reducing agent, yes, because the oxidation number of the tin changes from 0 to +4. Right. Again, within 10 seconds, if you, just by reading through them. However, if you could quickly see this one from the very start, Sn is the reducing agent because the oxidation number changed from 0 to 4. You could do it again always in less than 20 seconds. I've seen a number of these where they ask you what is the reducing agent in the reaction below. And of course the reducing agent must be something on the left. It cannot possibly be BrO3- because that's on the right. Forget that. It can't be MnO2 because that's on the right. Forget that. So it's a matter of this one or that one. And so what is the reducing agent? So we're looking at either Br-, which we know has an oxidation number of -1, going to there. And we know this must be oxidized because it's certainly not -1. It must be +7 or maybe +5. I don't know. And therefore Br- is being oxidized. So what is the reducing agent? Br- is the reducing agent. If you look at MnO4, we know from our past that that has an oxidation state of +4 from a previous calculation. And that this would have an oxidation state of actually much greater because with 4 oxygens and a minus charge, it's going to be +7 approximately, or thereabouts. So that is going to be reduced. So what is the reducing agent? Br- is reducing that from manganese +7 to manganese at +4. But as I said, eliminate those on the right, look at only those on the left, and choose the easiest one to decide on. I chose this one initially because I saw immediately this has a oxidation number -1, and this would have an oxidation number much greater. I hope that helps you understand oxidation and reduction and oxidation numbers. If you found this YouTube video helpful, please say you like it and subscribe to my channel and look at my other YouTube videos. Thank you.